Why is the volume of any pyramid 1/3 its base area times height? Let's prove this. In general, the volume of a solid is its cross-sectional area times length. So, for example, if we have a cylinder, the cross-section is a circle, so the volume is pi r squared h. If we have a rectangular box, the cross-section is a rectangle, so the volume is length times width times height. But for a pyramid, the cross-section is not uniform. If we take a square-based pyramid, for example, then you will always get a square cross-section, but the size of the square depends on how far up the pyramid you're slicing. Okay, so should we take the average cross-sectional area? Well, yes, but if you're thinking this is half the area of the base, then this would actually be wrong. You see, this would only be true if the cross-section was varying linearly. Although the edges are straight lines, and so you would expect the variation to be linear, it is the width that is varying linearly, while the area varies quadratically. To properly calculate this average cross-section, we'll use calculus. We'll align the central axis of the pyramid with the x-axis, and then slice it at a typical point x with a perpendicular plane. Take a square base with side length L, and say the sliced piece has a side length S, which depends on x, because it varies depending on where you happen to be slicing. If this portion has an infinitesimal thickness, dx, then the volume would be a of x dx, where a is the cross-sectional area. The plan then would be to sum up all of those differential volumes to get the total volume of the pyramid. The integral would go from 0 to h because we're slicing from the origin all the way to the point h0. Since we're taking a square-based pyramid, a is s squared, and s in terms of x can be found by observing that this line has slope L over 2h. This point belongs to the line, and its y-coordinate is s over 2. So s is L over h times x, and we can now square this equation, and we're ready to integrate. We'll take the constant outside the integral, this is L squared over h squared, compute the antiderivative, and substitute the bound. We can cancel the h's, giving us 1/3 L squared times h. We took a square-based pyramid here, but the same procedure can be repeated for any pyramid. And so, there you have it.